To understand virtual images, you have to understand the law of reflection. What the law of reflection tells us is that, before we get to this kind of scenario, if you just have like a mirror, right, and you have an incident light ray hitting this this mirror, then that light, if you think about the normal line to the mirror, which is the line perpendicular, this incident angle, I think it's literally just called the angle of incidence, will equal whatever that reflected angle is relative to the normal, right? These angles, sorry for my brother screaming, these angles are congruent, or whatever the geometry term is. They're the same angle, just like obviously like, you know, different directions from the normal, but they're the same angle. That's the law of reflection. And you might be saying, well, you know, mirrors obviously, you know, when you have light, they're gonna have the law of reflection, but you might be thinking, well, in order to see things, light has to bounce into your eye. And if the law of reflection holds, why isn't everything a mirror, right? If this wall over here, if that's following the law of reflection because light is reflecting off in my eyes, why don't we see, like, why isn't this a mirror, basically, right? Why isn't everything a mirror? Well, most objects are actually pretty rough. So if you think about, like at the microscopic level, or you know, for something, it's gonna look like a rock, right? And for a rock, well, it still kind of follows the law of reflection. If you have light coming in this way, it's just now this small section of the of that rock has a certain normal, and light will still reflect, right, with the same angle as the angle of incident, but now you have light, like if I draw a different kind of ray, right? This right here, it's a different normal for that small section of the rock. If you were to zoom in, and you would get like a different angle. So you could see the light, the reflected light will naturally be in all kind of different directions. You're not going to see the original like cause of that sort of like the original source, or like you're not gonna get a mirror, you're not gonna see the reflected light perfectly as the incident light. Now, to kind of show you like what I mean by like reflected light and how we see ourselves in the mirror, we're gonna look at virtual images, and why I guess necessarily something like a rock or like a wall doesn't show your virtual image. Let's say we have a person right here, right? He's looking into a mirror. We all know that we are going to see our reflection, right? It's a mirror. So let's think about this guy looking at his shoes. So if you think about the light, right? The light from his shoes is going to bounce off, hit the mirror, and go straight back into his eyes, right? So obviously, you know, you're gonna have light that's kind of scattering in all directions, but in order for our eyes to see it, there's gonna be one specific ray of light hitting right here, bouncing back into our eyes, right? If you follow this ray right here, it's gonna obviously reflect God knows where, and this light might reflect back to the feet, but the main light that we, the way that we see the shoe, it's going to follow this path where, if you think about the normal, right, this angle is equal to that angle, right? The incident angle is equal to the reflected angle. So here's the deal. In our heads, what actually ends up happening is this light, we kind of perceive it to like if we were to follow this ray backwards, our brain kind of perceives it coming from here, right? If you imagine the light ray coming through here, passing through the mirror, back into our eyes, that's how our brain kind of thinks of it. It's like, I guess it's kind of like an optical illusion. There's no light actually here, but the way that it reflects and then enters our eyes kind of treats it like there's light actually being reflected from here. And then that's where we see, like actually before we actually start drawing the person, yeah, that's how we kind of see, like that's why we see our feet over here, right? Like we literally perceive it like light is coming like through the mirror. And I mean, we could do this for all sorts of parts of his body, right? Let's think about his hand right here. So his hand, it will kind of look like this, right? And if we follow that ray backwards, his hand is going to appear right here, right? We can do the same thing for his kind of his pelvis. If we think about this light, right? And then we can even start drawing out kind of like some of this, right? So this is his pelvis. And I didn't draw this quite to scale, but it's fine. If you think about the hand right here, it would kind of reflect like so. And I'm not drawing. You can see it's kind of being screwed up because I'm not drawing the angle of incidence perfectly with the angle of reflection. So if you were to like do this by hand, it's gonna look a little wonky. Also, I also just gotta look at the image more and be like, hey, there's shoulders here. But point being, you get a virtual image by the light kind of seeming to come through the mirror, even though the mirror is not producing any light, it's just reflecting it back. So then this would be where the feet are coming from, and I drew this terribly wrong, but hopefully you get the basic idea of how you see your reflection. Now, a couple things to note. So this is the left foot, right? This would be essentially the left foot, even though it looked, yeah, this would be the left foot, right? No. Wait, oh, this is so weird. If you're seeing this, then this would be your, this is his left foot. He would perceive this as like on his right side, but this would also be his left foot. But you could see they're opposite sides, like they're both like closer to the mirror, right? Well, these distances right here, they're gonna be the same. So if you look at this distance and you look at this distance, if I call this SI for like the distance from like that, I guess I'll call this SR for like, this is the real thing and this is the virtual side. So real SV, they're gonna be the same distance. Maybe intuitively that kind of makes sense, but if you want to really prove it, because you know we're all math nerds, I guess, you want to prove it, the way you would kind of go about doing it is that, well, this angle, right? Well, these are both right angles, right? Because this is the horizontal, this is the vertical. This angle would be the same as this angle because if you think about, like, if you were to extend this line, then this angle would be the same as that angle, and then you can probably do some right triangle stuff, and these two angles would end up being the same. And if these two angles are the same, and then this we can call a distance h, then we know, like, let's say this is an angle phi, right? We could say that, hey, cosine phi is going to equal, and let's call this hypotenuse L. We're going to call this h over L. Then we know, because these are the same angles, the cosines of these angles have to be the same. And if both share the same adjacent h, then the hypotenuse has to be the same, right? If this is the same and h is the same for both, then L has to be the same for both. And I mean, this isn't, like, this relationship isn't always entirely true, right? Because if you think about, well, if this had double the height, then cosine theta could still be the same if you had double the length. But we know the height is the same. They share the same height, same length here, and you can use Pythagorean theorem to show that, yeah, these both would be the same. So yeah, that holds for like any distance, right? Like the distance from the pelvis to the mirror is the same as the distance from the mirror to the virtual, or like the perceived distance, right? So that's why when we did that lab in class, when you think about a, you know, if you think about a, like if you thought about the pencil, right? We had a pencil and we had the mirror. That was like halfway. Well, and then if you put another pencil equidistant away, right, it would look like the reflection would kind of match up with the other pencil. So it looked like all the same pencil. And that makes sense, right? Because whatever your virtual image was, right? Because from your perspective, right, if this is your eye and you're seeing this, everything from here is the virtual image, right? Everything below the real pencil on the other side. So for the virtual image, if you had the real pencil on this side equidistant from this pencil relative to the mirror, then the virtual image would line up because, yeah, the virtual image would also be equidistant from the pencil to the mirror, right? So that's why we got that illusion. It has to do with this principle. So why doesn't, like if you had a wall, why does a wall not reflect you? Well, if you had light coming in through here, like this might be, let's say this light reflects like so. Well, the light over here, should I just draw all these, should I erase all these rays? Maybe I could show it like that. Sorry about that. Mr. I don't know who you are. Let's say you have light hitting here. Well, the normal here might be like, I don't know, like so. And then this light would scatter like so. And then if you had light coming from here, maybe this normal is like this, right? So you have light kind of coming back here. The light would just scatter and diffuse, and you wouldn't get your exact image. You would still see light bouncing off, but it would just reflect the natural grooves and shape of the wall itself, not yourself. So hopefully that makes sense. Thank you for watching, and let's have some fun making virtual images. Am I right? I don't know how to end these things. I'm not really, I don't know.